Our next speaker is Professor Frank. So he should.
Yeah. Do you see my slides?
Yes, we do. We do. Thank you.
Okay, wonderful. So,
so you can start. Yep.
Yeah, and please interrupt me if I'm running over time. The timing has not been well rehearsed.
Yes.
And the talk has
when you have 10 minutes left, we'll let you know.
Yes, very good. The talk also has segments, so it makes sense even if I end early. So I'll want to talk about quantum algorithms and specifically about a few results related to optimization problems for the number partitioning problem. And this is work done with various people in my group. And you see the canteen of our research center. If we look at the status of quantum computers, currently the sensitivity to errors that quantum computers have is what is limiting progress. Even when quantum computers become more mature and hardware just becomes a lot better engineered, we do not expect this to go away. Because quantum information, while you compute, has an analog component in it. So it's always sensitive against small errors. And also, we always need to isolate quantum information against the environment, because if we don't do this, it goes classical, which is why what you see on the right is happening. People build large cooling systems for essentially isolating quantum processors for noise. And in fact, if I'm looking at current error rates, then per 2-qubit gates, which are typically the hardest operations, we have error rates about 0.1%, which means that when we do 1,000 applications of those gates, the algorithm will, with high probability, be wrong. And the benchmarks, like the Google Quantum Supremacy benchmark, are all based on tricks to learn to live with this. But when we look at really applied benchmarks, at problems, at algorithms for benchmarking quantum computers that solve problems people care about, they typically only use the small part of those large chips. So even going above 50 there would be a major breakthrough. Let me remark that oftentimes in the media, you see roadmaps on the size of quantum computers want to build. And they talk about roadmaps that reach 2 or far above 1,000 qubits. But in the current setting, with those error rates, the roadmap on how to lower error, more important ingredient, you could say a little bit kind of, if you like, a bit more strong words. People have made chips with 1,000 Josephson junctions in the 90s, but they were not qubits. But this is a hard thing. So what the community does instead, this way I can switch my slides, okay, is to hybridize quantum and classical computers. So we typically, this comes in a setting where we use a quantum computer or even a quantum simulator to take a quantum algorithm, parameters, then use the quantum computer to compute a cost function that is hard to compute on a classical computer, but easy on a quantum computer, then measure the cost function, optimize the algorithm on a classical computer, and send it back to the quantum simulator. And this is promising for quantum computers with high error rates, because the quantum computation that you have to run before you read out is very short. Technical term is it's very shallow. And then we can reset the quantum computer. Reset is a procedure that has very, very little error. So then we have removed most of our errors. The problem for this is that proving quantum speed up mathematically there is very difficult and only restricted to very isolated cases. The appeal of studying this is that these are typically all optimization problems, right? You want to prepare a cost function in a state that corresponds to the minimum. You use the classical computer to find the minimum. And optimization, if you want, is the most important problem in computer science. The technical terms is that the optimization problems are NP complete. So those are the hardest problems that computers reasonably can address. This is a kind of very superficial definition of NP complete. Now, I will introduce to you the QAOA algorithm, which probably many of you have seen, the quantum approximate optimization algorithm, and then show you two results of our groups. One is to reduce it to a sampling problem where you only need to run the QAOA algorithm once. And then I want to show you a quantum-inspired classical algorithm that is similar to QAOA, and that can help us understanding in which cases QAOA can give us speed up. But let's take a step back and let's just remind ourselves about variational algorithms for optimization. And in fact, the first quantum algorithms for optimization that have been proposed in literature are adiabatic algorithms. If you look on the right, it depends on a setting where you have a Hamiltonian describing your quantum computer that has two terms. HD, the driver, this is typically a superposition of sigma x Pauli operators, and a problem Hamiltonian, HP, which is typically diagonal in the computational basis, so it can be decomposed into terms that contain products of Pauli Z operators, giving us the most general diagonal term. And our goal is now to find the binary number that minimizes the problem Hamiltonian, and that basically encodes a hard combinatorial optimization problem. So why is this hard in general? On the upper left, you see a situation in the right panel, so the blue panel in the middle. I think my pointer is kind of not working, so I just explained this very verbosely. So you see a problem that typically, when you're drawing the landscape of potential binary numbers that solve an optimization problem, it can have a lot of local minima, which means if we use a local search algorithm, we will get stuck in the local minimum, we won't find the global minimum. Adiabatic quantum computing, now if we go back to the upper right, takes a function A of S, this is called the annealing schedule, and we assume it's simply linear going from 0 to 1. We are not studying more sophisticated annealing schedules in this talk, even though they are important. And we basically switch the driver Hamiltonian off slowly, and we switch the problem Hamiltonian on slowly. And then we can appreciate the figure on the upper left. Namely, we're going from a minimum in a very simple landscape to a minimum in a very complicated landscape. And according to the adiabatic theorem of quantum mechanics, if we do this slowly enough, then we stay in the ground state. Now, for the adiabatic theorem to hold, it's important that the driver Hamiltonian and the problem Hamiltonian are non-commuting. And secondly, the speed, you would say that quantum computers are supposed to be fast. Now we're talking about adiabatic. The speed that we can take is essentially controlled by 1 over the energy gap delta between the ground and the first excited state. So to evaluate quantum speedup, we need to check how does the gap shrink with the problem size. That's a hard problem on its own. I want to kind of remind you of a different take on this, because one other challenge here is that the problem Hamiltonian here has to be carefully built into the quantum computing hardware, which is not suitable for, say, gate-based quantum computers. And this is why people came up with the quantum approximate optimization algorithm, or QAOA, which is essentially taking adiabatic quantum computing and introducing feedback. So we take an algorithm that we are simply writing down in time. Time runs as usual from left to right. And we are now taking the driver Hamiltonian and the problem Hamiltonian and apply them alternatingly in the shape that you see in the equations on the upper right. So we apply the driver Hamiltonian for a certain time, dimensionless time we call beta k. We do the same with the problem Hamiltonian for dimensionless time gamma k. And in order to simulate the adiabatic algorithm, we could discretize this in the form of a staircase. And then we make a bit of a discretization error, but that is usually quite forgiving. But then on top of this, we can, if we're not happy with the outcome, use a classical computer. So we measure the outcome, we use classical optimization to adjust the numbers beta and gamma, and to make the error smaller. Now, one advantage here is that now we do not need to build everything into hardware. If we have a, like an IBM machine, a universal quantum computer gate type, we can take these two steps, the drive step and the problem step, and compile it onto our hardware. So this gets us quite a bit more flexible. And we can use this optimization to work with the speed up. However, to make really a good match, we need to have a large number of steps, a large N, and that is often a problem because I've just told you that we cannot really run long algorithms on our limited quantum hardware. So what is known about convergence is this is likely capable of getting a square root, like in the Grover algorithm, a square root improvement, which is something we shouldn't underestimate, but people speculate about exponential speedup. But for exponential speedup, there's actually no proof. Now, if you look at the original QA paper, and I'm unfortunately not very good in putting in references, that was a paper by Fari. It is telling you that for the max cut problem, it's the problem from graph theory, there is speed up, but then there was a later exponential speed up even, but then there's a later paper by Hastings that disproves this by finding a new classical algorithm. So what I now want to show you is two results from my group where we at least want to make some progress in order to, in the sense of simplifying the problem of analyzing the speed up from QA. And the first thing is a paper that I've written with my student David Hedley, which just appeared on the archive, which is to avoid closing the loop. And for this, we are going back to the driver Hamiltonian, the sum of sigma x that we have introduced in the previous slide, that makes you essentially tunnel between different solutions. This is very nice because it can be simply implemented, but it's a bit biased in the sense that flipping one qubit there is really easy. Flipping more is really getting more difficult. How can we see this? If you're looking at the equations on the left and the bottom, we're simply taking now e to the minus I beta times this driver Hamiltonian. Beta is our QA parameter. And we write this out. This is simply a product of single qubit gates, which all go as cosinus beta times minus I xi. Xi is the Pauli X operator on qubit I times sine beta. And if I now take the matrix element between two basis states S and T, so S and T are binary numbers, it has the form cosine beta to the n minus d times minus I sine beta to the d. N is the number of qubits and d is the Hamming distance. So the Hamming distance is the number of bit flips between two numbers. So this is introducing an artificial structure in your problem. It keeps your problem very local. Now, alternative, we can introduce the Grover driver, which is shown on the upper right, where we also take a term that is very off-diagonal. We essentially take a reflection of the superposition of all terms, of all input values. This corresponds to the Grover algorithm mixing term. It has no bias. It's treating all binary numbers the same, but it's quite hard to compile because to write it up, we can break it down into this product of 1 plus Zn times 1 plus Zk products. And out, we see that we don't only get terms that are quadratic in sigma z, but also higher terms. So this is very demanding on hardware, but we can use it as a tool for proving. And this is what we can do. If now we have this complicated optimization landscape, what we can do is we completely disregard the order. All we need to do is some cumulative statistics. So if you want to optimize something, we simply count how many of these are typically low, how many of these are typically high. We get a cumulative distribution function, and we can do this without actually solving the problem, but just knowing the statistical properties of the system. We can do this for a typical problem rather than the problem itself. And then we can automatically evaluate the performance under a Grover driver. And we have done this for the number partition problem, which is actually a practical problem. We're giving a set of numbers, and we want to split them up such that both sums are equal, or that the difference is minimal. And this is actually practically relevant if you, for example, have a computer with two CPUs, and you have some computation jobs that you want to distribute evenly over the two CPUs. You would solve this problem. Of course, practically, you would take a larger version, but it's a relevant problem, and it's NP hard. And we simply assign qubit up or down to saying we put it into the left or the right partition. This is the cost function. It's a quadratic cost function. And here we can now take this cost function. We can realize that this has a chi-squared distributed probability. This is a known statistical property of this problem. And it's at least describing the average case. We Fourier transform it, we get the average function. We simplify it into the QAOA optimization landscape, and we can minimize. And we right away find out that if we do a one-step QAOA, what are the angles that we need to run it optimally? We never need to iterate. And that makes using this a fair bit simpler. And we can show that if we go from depth 1 to larger depth, we very easily get a landscape that converges. We have assumed, because we're doing statistics, that we have a large version of the number partitioning problem. But we see that if we go to n equals 12, we are actually already at the large n limit. So we can practically avoid doing feedback in QAOA with the Grover driver. And we're not so sure whether people would practically do it, but I think it's a nice tool to actually study this algorithm. In the second half, let me jump over the caveats, because I actually already said this. And you see that I got these slides for my students because he's doing a lot more optimization that we can do. Let me share a second result that we're really excited about, namely a quantum-inspired classical optimization algorithm. So these are the natural enemies of the proof of quantum speedup. But of course, we want to be honest in understanding where does quantum speedup happen. And if we get speedup without quantum mechanics, we should be happy. So I will now show you a classical optimization algorithm that is quantum inspired for n spins. And I'm going to show you that for two problems, namely the Sherrington-Kirkpatrick spin glass, which is a good kind of a random, generically difficult problem, and the number partition problem, we can, this shows excellent results. It's polynomial in time in a classical computer. And we can actually even predict when it fails. So we can, if you give me a problem, I can tell you efficiently what comes out with this algorithm. And I can tell you if it fails, and only if it fails, you should actually go to your quantum computer. How does this look like? Well, we take our Hamiltonian of our spin system, and you see the same ingredients as before. We have beta, which is now time dependent because we have continuous time. We have gamma, which controls our problem Hamiltonian. And all I have done is I have replaced the quantum operators sigma x and sigma z by numbers, which have a classical Poisson bracket relation. So I have replaced the qubits by classical compass needles, or in other means, I'm saying that the single qubit physics is quantum, but there is no entanglement in the system. There are classical correlations, but no entanglement. And then we discretize beta of t and gamma of t, and we solve the classical equations of motion. And this is now an equation system of small size. It doesn't contain the exponential memory that the quantum algorithm uses. And we can actually, when we discretize it, solve it exactly. The quantum solution vector in the end is shown on the upper right. And it's a product of very long matrices, of matrices corresponding to the time step that you can at least put on your computer algebra system and solve. And we call it mean field QAOA because the key ingredient is this number mi of k that is in the middle of the slide. And if you go back to the Hamiltonian, you see what it does. We're picking out one spin, and we are now checking what do all the other spins do on it what is the average field produced by the other spins. So this is very much in the spirit of mean field theory and statistical physics. We take the effect of all the other qubits and we are replacing it by one number. So in this sense, this is mean field theory. And to solve this, again, this goes as quadratically in time. So this can be efficiently solved in a classical computer because it doesn't contain entanglement. Now here we tested this first on the Sherrington-Kirkpatrick spin glass. If you don't know, if you know what this is, you know it. If you don't know what this is, it's essentially a random version of the Hamiltonian that I've shown to here, where the Jij's are picked in a specific random way. It is hard to solve classical. And of course, Giorgio Parisi got the Nobel Prize for his studies of this problem. And one thing that we see is that the average energy of the system, E star, minus the size of the system, for a large system goes to a universal value, epsilon p, which is this number 0.763 and so on. And in the best classical algorithm, which is very hard to run, the error goes as n to the minus 2/3. For our algorithm, it goes n to the minus 5/8. So it becomes pretty close, and it's a classically efficient algorithm. Secondly, we can also show that, so this is the model again. The average of Jij squared goes as 1/n, and we are reaching this, this universal number. And again, we are reaching it quickly. But moreover, the deviations from this are very well described by our algorithm. So here we see in orange, the exact deviation from the mean, and in blue, the one that our algorithm is finding. And you see that they are very, very close. And they are making the red line, the Gumbel distribution that you're expecting here, a little bit more symmetric. The model becomes a little bit more Gaussian. So also here, our quantum-inspired classical algorithm behaves very similar to the best known classical algorithms. If we are looking at the probability that it fails in a small exponential tail shown on the right. Now this tail doesn't look small if you look at the picture, but remember this on the left is a log scale. So we have a couple of rare events that drop exponentially in the size of the system when this algorithm fails. So we have now, this is a quantum technologies conference. I'm talking about a classical algorithm. But what does this tell us about QAA? The chairman is getting up, and I'm getting close to my last slide, is the following. We can now also take the QAA algorithm, the full algorithm. We can write it as a path integral, as a spin path integral. It contains the Hamiltonian and a Berry phase term. Here I'm showing you the action. And the mean field solution comes out as the saddle point of the action. So in the same way as we go from quantum mechanics to classical mechanics by a saddle point, we can go from a quantum algorithm to a classical algorithm by taking a saddle point solution. And if you're looking in a path integral textbook, you know that if you do a saddle point, you can calculate the noise around the saddle point. And if you can estimate the noise around the saddle point, you know whether it will work. And here is a case where we know that that mean field QAA works really well. Namely, these parameters here are so-called Lyapunov exponent. And as long as they're smaller than 1, they are telling you that mean field is working very well. And here you see they're going up to 0.2. So this is an easy problem. This is a problem where it doesn't make sense to start your quantum computer. You should stay with mean field QAOA. And here is the second case where the exponent explodes at this value S3. Here we see that this is a problem that a classical algorithm cannot solve efficiently. Here is a chance for quantum speedup. And for the experts in the group, this corresponds to a transition from ergodicity to many-body localization. So we can understand this pretty well. And what we think this does is it's giving us a new class of problems and a new way to say, here is a quantum algorithm that we can efficiently classical simulate. So if you want to look for quantum speedup, please look somewhere else. So in summary, I told you a little bit about the QA algorithm. I showed you that when you have a Grover driver, it doesn't need numerical optimization. And I've shown you mean field QA as a testable quantum-inspired classical algorithm that shows you that in some cases, the QA solutions can be efficiently simulated. So if you want to look for quantum speedup, please look for somewhere else. The chairman got up. I think I've kept reasonably in time, and now I'm looking forward to your questions.
Thank you very much. Actually, by my time, you still have 6 minutes. And but we'll take questions now.
So there was a question about the driver and the problem matrix in this context.
Yes.
So I didn't know what was the context, whether it was QAOA or adiabatic.
So the person, he wants you to explain to him more about the driver and problem matrix.
Yeah. So in the problem matrix, in adiabatic quantum computing and in QAOA, these are both meant to solve optimization problems and classical optimization problems, because when we start a quantum computer and when we read it out, the output is classical. So the goal of the algorithm is to find the binary number S that minimizes a certain binary function. And now we take this binary function and break it down in a matrix. We can do that because this is simply a change of basis. You typically, for example, your binary function could be a optimization problem. It could be, sorry, a combinatorial optimization problem. So you're saying, I have a problem S1 and S3 should be true, but S3 XOR S4 should also be true. And we can break this down into binary statements out of a couple of bits, and we can write this down as Hamiltonian. Or we could, and this will always work because writing down an arbitrary binary function versus writing down an arbitrary diagonal Hamiltonian has the same number of degrees of freedom. Now, in the qubits context, because we want this to be a classical problem, we always take this in the sigma z eigenbasis. So the zi and zj are still always sigma z bases. And our goal is now to find the bit string to get us to this minimum. Now, in QAOA, we are working with the absolutely same matrix. We want to find the minimum of this matrix. The driver Hamiltonian is what is making us jump between two binary numbers. So in the qubit context, it needs to make us jump between two computational states, between two binary numbers. And here we take something that is off diagonal, and conventionally it's a combination of xi terms. And we call this the driver because it drives transitions. And in standard QAOA, as invented by Eddie Fari, again, H driver is the same term as here. It's a superposition of xi terms. I don't know whether this answers your question. If not, feel free to re-ask it or to re-ask a very precise version.
Okay, so Frank, please, I have a couple of questions, but they're more philosophical.
Okay.
So the first question has to do with, do you think you can couch every problem as an optimization problem?
Computer science tells us that, not all problems, but a large and important class. So in computer science, NP-complete problems are those problems that are hard to solve. You know, there's a question whether P was that we think that are hard to solve, but where the solution is easy to check.
Okay.
And realistically, those are among the hardest interesting problems. An example is factoring into prime numbers. Yeah. If I give you two prime numbers, you can easily calculate the product. If I give you a product of prime numbers, it's kind of the prime factors. Yeah. And there is a well-established, proven result from theoretical computer science that a group of optimization problems is what is called NP-complete. That means that any problem in NP can be efficiently mapped onto this NP-complete problem.
Okay.
So, and those are optimization style problems. Thus computer science tells us that at least everything in NP can be broken down to this. And one of the big questions here around these algorithms is that the Shor algorithm, you know, the most famous quantum algorithm, solves factoring. Factoring is in NP, but it's not NP complete. Okay. And there is a lot of speculation in the literature what quantum computers can do to NP complete problems. Many people believe that they cannot provide exponential speedup, but it's not completely clear. And of course, we still want to see, are there other problems in NP where this, which are not NP complete, where this could give speedup?
Okay. Yep.
So it's always tricky because computer scientists have a very unusual way to think about efficiency. Yeah.
Okay. The other philosophical question is this. Thank you for that. So if you have a landscape like the one you showed, and even if you a quantum algorithm or quantum computing, how do you know you got to the minimum? Like, because typically tell students that because you have to check it.
Yeah. So in some in these NP complete problems, one of them is a three set is called three sets. These problems are all extremely abstract. They more look like, you know, a quiz in the newspaper. But a three set is basically you take a number of logical statements and you check, can they all be simultaneously solved? Now, what you can do is you can, for example, try to find the minimum of the error, and then you check, is the error equal to 0? But it's not always possible to do this. So verifying a solution is not always possible. In many cases it is, but not all of this.
Okay. Yeah. Thank you. There are two more questions, one from Jonah and one from Honoring.
So the software that we used for adiabatic quantum computing was homemade. Barren plateaus, if one uses a chemistry-inspired ansatz, that is tricky. I cannot give you a good insight that no, I cannot give you a good answer to this. We are using noise-induced barren plateaus, but I don't have a noise-independent answer. I'm sorry.
Okay, thank you. Thank you very much. In Kigali, does anybody have a question? Okay, so let's thank Frank once again. And then from
Thank you very much for having me. And I'm sorry I couldn't make it to Kigali, but my life currently suggests to me that I should stay away from as much travel as I can. But yes, thanks for having me.
Thank you very much for joining us. And so now we'll take a break and go for lunch. And then we'll be back at 3 p.m. Kigali time, I think. I need to check. Yeah, so I think we'll be back 3 p.m. Kigali time. And our next speaker will be Professor Steve Gervin from Yale University in the US. Okay. Thank you very much, everybody. And let's thank all the speakers once again.